This video lecture addresses image acquisition. Understanding how an image was acquired and the underlying technology helps the analyst better use the data. In part, image acquisition is critical as it helps the human user understand how remote sensing images differ from what humans are used to seeing from the ground. Remote sensing captures data from an overhead view and can include radiance outside of the visible spectrum. Often, remotely sensed images have unfamiliar scales and can be presented at unfamiliar resolutions. After viewing this lecture, the viewer should have a better understanding of spatial information and how it is collected and analyzed. In recent years, there has been a near-complete transition from analog to digital aerial cameras. There are four basic components of cameras, including the lens, a light-sensitive surface, a shutter, and the camera body. The lens gathers reflected light to form an image, focusing it on the focal plane. The light-sensitive surface records the image. The shutter controls light entry and controls the length of time of light exposure. The camera body holds all of the components in proper position and must be light tight. There are two major geometries common to vertical aerial photography, which are oblique and vertical. Oblique images are captured with cameras oriented to the side of the aircraft. There are two types. High oblique aerial photos show the horizon, whereas low oblique aerial photos do not show the horizon as the camera is aimed more towards the ground. Advantages of oblique imagery include showing a large area in a single image and having a familiar view like from a tall building or a mountainside. Some disadvantages of oblique imagery include drastic changes in scale from the front to the back of an image, difficulty in measuring distances, area, or elevations, and not being widely used for analytical purposes. In contrast, vertical images are captured with the camera aimed directly at the ground surface from above. Advantages of vertical aerial imagery include that the images offer a map-like view, present predictable geometric properties, and are commonly used to measure distance, area, or elevation. One major disadvantage to vertical aerial imagery is that objects are more difficult to recognize. It is also important to note that while we describe images as vertical, few are truly vertical in the orientation due to shifts and complications in the flight. But we recognize that vertical images are within a few degrees of vertical and, for all practical purposes, are considered vertical. Aside from differences in geometry, there are also many possible band combinations for remotely sensed imagery. For example, black and white infrared imagery captures energy in the near-infrared region, which is largely considered one of the most valuable regions of the electromagnetic spectrum. Black and white infrared imagery is largely free of atmospheric scattering, showing vegetated regions and land-water distinctions. Another possible band combination is panchromatic imagery, which literally means across the colors. In panchromatic imagery, all bands within the visible spectrum are presented across the colors so that there is no separate channel for the three primaries, that is, blue, green, and red. Panchromatic imagery provides a black and white image, and the added detail of combining the visible spectrum provides more information than the colors would. In the natural color model, the imagery is displayed similar to the human visual system, where blue is applied to blue, green is applied to green, and red is applied to red. One obvious advantage is that natural color imagery is similar to what we see, so it is easy for the analyst to interpret. One disadvantage to natural color imagery is the atmospheric scattering in the blue region of the spectrum, leading to limitations at high altitudes. Another possible band combination, false color infrared imagery, is useful in part due to human limitations of the visible spectrum, allowing reassigning of color, that is, blue, green, and red, to other portions of the electromagnetic spectrum. For example, blue is filtered and green is displayed as blue. Red is displayed as green, and near infrared is displayed as red. This band combination was developed as camouflage detection film in World War II, in part to help detect areas on the ground that were designed to look like vegetation to the enemy. False color infrared imagery greatly reduces atmospheric effects by filtering blues and clearly displays vegetation and water bodies. An orthophoto is essentially an aerial photo that has been corrected to eliminate error and tilt and relief displacement. As the U.S. Geological Survey USGS 2013 notes, quote, "A conventional perspective aerial photograph contains image displacements caused by the tilting of the camera and terrain relief topography. It does not have a uniform scale. You cannot measure distances on an aerial photograph like you can on a map. The effect of tilt and relief are removed from the aerial photograph by a rectification process to create an orthophoto. An orthophoto is a uniform scale photograph. It is a photographic map. Since an orthophoto has a uniform scale, it is possible to measure directly on it like a map. An orthophoto may serve as a base map onto which other map information can be overlaid. One band combination example for multispectral imagery is 742, where one region from the visible spectrum, one region from the near-infrared, and one region from the mid-infrared are combined to display false colors, but the image resembles a natural appearance. The 742 band combination is common in geological, agricultural, forestry, and fire management analyses. As Esri 2014 C notes, quote, "This band combination, 742, provides a natural-like rendition while also penetrating atmospheric particles and smoke." Another common band combination for multispectral imagery is 451, where blue, mid-infrared, and near-infrared radiation are displayed. As Esri 2014 B notes, this band is used for vegetation studies. A third example of band combinations is 754, which does not include energy in the visible spectrum. Because of this, the 754 band combination offers the best atmospheric penetration. As Esri 2014a notes, quote, "It can be useful for geological studies such as the moisture characteristics of soil." A fourth common band combination is 543, in which healthy vegetation appears from bright green to dark green, and soils are depicted in mauve, tan, and brown. Esri 2014d. Band combination 543 is often used in, quote, "timber management, infestation detection and management, and crop monitoring." The following references were used in developing this video lecture.